Hi, my name is Rayna Liu. Today I'm going to talk about the hourly traffic volume forecasting. As first, I'm going to do the introduction, then I will take the brief description of my time series datasets. After, I will check the stationary and do the time series decomposition. Then I'm going to develop multiple models like the Holt-Winter methods, multiple linear regression, ARMA, ARMA, and SARMA, and some of the base model. By analyzing their residual and focus area to select the best model for the forecasting of their hourly traffic volume. Traffic volume forecasts are used by the many transportation analysis and the management system to better characterize the rates of their fluctuating traffic pattern. The purpose of this term project is to find the best model to forecast your hourly traffic volume by developing, analyzing, and compiling the couple of the models. For the description of the dataset, I'm going to talk a bit about the data proposing and take a look of the traffic volume over time. The ACF and the PACF of the traffic volume and the correlation metric of the datasets. So this is the hourly method in-state traffic volume datasets, which include the weather and the holiday future from the 2012 to the 2018. There are no missing variable, but there is the missing times. To handle the missing data, I split them by the hours and replace by the missing data with the mean hour traffic volume. After proposing procedure done, this dataset contains the 40,575 instances and the 9 attributes. The dependent variable is the traffic volume, and the independent variable are the rest of their attribute except daytime. Here is the traffic volume over the time. Since the large hourly change of the dataset showing the all instance will miss up some information, so I only show the 200 sample here. From the ACF plot, we can see that this dataset has a strong seasonal pattern with the period of the 24 hours. In its correlation matrix, only 3 to 4 features have the multiple to strong correlation with each other. The rest of the variable almost no correlation. Then, for the stationary, I'm going to check the stationary of the datasets by doing the ADF test and plotting the rolling mean and the variance over time, applying their seasonally or no seasonally differencing to make the dataset become the seasonary. As the ADF test and the rolling mean and the rolling variance say the dataset is stationary, but the ACF show the raw dataset has their seasonalities and is not stationary. Since each dataset has daily seasonal pattern and a weekly seasonal pattern, using the seasonal differencing with the interval 168 plus the first order no seasonal differencing will make the dataset completely stationary. Then I'm going to do the time series decompositions by using the STI decomposition method to see how the strength of the trends and the seasonality have. Also plots of the raw data vs the trends and the seasonality adjust datasets. This dataset has the strong constant trends and the strong seasonality which does not well with the level. Here is the plot of the raw dataset and the trend dataset and the seasonality adjust datasets. Let's develop the first model by using the Holt-Winter seasonal method. The Holt-Winter method does a good job on forecasting these stronger seasonal datasets. For develop their multilinear regression model, first I'm going to do the collinear detection, then do the feature reduction to generalize the final model, then check the capability of their model to do the one-step forecast, analyze the residual. There is one of their single value close to 0 and the condition number is much higher than 1000, which means one of their more future is correlated, the collinear except in this dataset. To do the feature reduction, using the backward stable regression reduce the future space dimension. First, generalize the multiple linear regression model contains the all-potence predictor by using the OLS function, then remove the predictor at a time. Remove the predictor based on which has the highest p-value. Based on the observation from their heat maps, only 2 features have the really strong correlation with the traffic volume. They may be 2 or 3 features after feature reduction. Since the p-value of the all coefficients are much less than the 0.05, all the coefficients in the final model are significant. Also, since the F statistic is large and the p-value of the F test is much less than the 0.05, which means the final model provides a better fit than the intercept only. However, the AIC and the BIC are large, which means the multiple linear regression model may not fit the dataset and they're not well for the forecasting. The R-square and adjusted R-square are 0.74, realized 74% of the dataset fits the model. Let's take a look of the one step ahead forecast of the multilinear model. It's obviously that this model do not do well on forecasting this traffic volume. Let's do the residual analysis to see what happened. From the residual analysis, its variance and the Q-value are also large, and the ACF of residual still shows the opposite pattern, which means this model had not captured the seasonality pattern in this dataset. Then I'm going to divide the ARMA, ARMA, and the SARMA model. First, do the auto determination, then estimate the parameter of the ARMA model, then do the analyze. Since the seasonal period of this dataset is 168, a pattern with the constant column and the row of the zero must be displayed on the column and the rows multiple of the 168. So it cannot show the JPEG table over the 100 column. Since for this dataset, I could not estimate the order of the SARMA model by the JPEG table, but I can estimate the order of the ACF and the PACF plot. The PACF showed the decay scroll the seasonal lag k equal to 168, 336, and the ACF shows a no zero autocorrelation as the first seasonal lags equal to 168. This reflects the final model include at least of the seasonal ARMA model has the MB order. Also, since the PACF and ACF have no zero at the lags k equal to 1, 2, and 3, and the additional zero correlation at the lags k equal to 165 to the 171, I can estimate this is the multiplicative of the no seasonal ARMA model times the seasonal ARMA model. It maybe look like here. But in actually, whatever 168 or 171 are too large to generalize the model. So I tried a smaller number in ARMA model and find the ARMA 22 model has the best performance with the smaller AIC and the Q-value of the residual. The confidence interval of all estimate parameters do not contain zero, which means the estimate coefficient is important. And there is the no same rule of the numerator and the denominator, since there are no zero pro cancellations. Since the Q-value of residual is larger than the chi critical value, it shows the residual are not wide, which means that except the seasonal pattern is still not captured by the model. Since the residual of the ARMA 22 procedure is close to zero, which means it's the unbiased estimator, the ratio of the variance of the residual error vs the variance of the forecast error is close to 1, which means the model did a good job on focusing on the stationary dataset. ARMA 22 model could only forecast the stationary dataset, so I convert the ARMA 22 process to the SARMA model, which could use for forecast the traffic volume of the raw dataset. As the graph looks like, at first the forecast is not bad, but after 1 week, the forecast traffic volume is decreasing over the time. Then I'm going to develop some base model and plot the forecast vs the test sets. This one is averaging method. The forecast of the all future value are equal to the average of the history data. For the negative forecast, we simply say the all forecast to be the value of the last observation. In the seasonal naive method, each forecast to be equal to the last observation value from the same seasonal of the year. For example, with the hourly data, the forecast of the all future 7 p.m. value is equal to the last observed 7 p.m. value. For the drive method, it's equal to drawing the line between the first and the last observation. It shows a line for the SES method of each step forecast. For the holistic learning trends method, it shows the line too. Then I'm going to do the final model selection. To do the comparison of the 9 forecast method, we can see the seasonal narrative method has the minimum Q-value and the MSE of the forecast error. Its forecast can simulate the pattern of the test sets very well. Therefore, the final best model is the seasonal naive method. In its case, I use the h-step-ahead prediction function as the forecast function. For the seasonal naive method, the h-step-ahead prediction function is over here. In conclusion, the naive seasonal method is as helpful for your highly seasonal data as my traffic value data. My final model, joined by the naive seasonal methods, can predict the future value correctly. I think the limitation of these methods cannot count for the week-to-week change in level. And thank you for listening.